Hey y'all, my name is Elijah Johnson, and this video will cover Lab 1 constant velocity. The purpose of this lab is to observe the motion of an object moving at a constant velocity and compare my experimental data with a computational model. We'll use physics principles such as Newton's first law of motion and kinematic equations to analyze this behavior. So, to model the motion, I use Newton's first law, which states that if no net force is acting on an object, it will continue moving at a constant velocity. I analyze the motion using the tracker software to extract the object's position over time and then compare that data with my predictions from my computational model. I recorded a video of a Gatorade bottle rolling at a constant velocity. Using Tracker, I analyzed the object's motion frame by frame, tracking its position over time. The data extracted from Tracker was then used to plot position versus time. The analysis showed that the bottle moved at a nearly constant velocity of approximately 0.88 meters per second, which was slightly lower than the predictions from my computational model, likely due to small real-world forces like air resistance and friction. In the computational model, I applied Newton's first law by setting the net force to zero. The mass of the bottle was 0.355 kilograms, and the velocity was set to 0.88 meters per second based on my experimental data. Since the model assumes no unbalanced forces acting on the bottle, it moved with constant velocity. And you can see that in the code. So when I change this around, I changed the mass, and then also this has the initial velocity of 0.88 meters per second. Delta T is the same from Tracker, and then the net force was zero. So I plotted the observed data from Tracker and the predicted position versus time from the model on the same graph, in which you can see right here. So the predicted model, which assumed no external forces, showed a slightly higher velocity compared to the real-world data. This difference can be attributed to air resistance and friction, which slightly slowed down the real object. However, the overall match between the experimental data and the model was close, confirming that the motion was nearly constant. So the key principle here is Newton's first law, which again states that an object will remain in motion with constant velocity unless acted upon by a net external force. In this case, small forces like air resistance and friction slightly affected the observed motion, but the overall behavior remained close to the constant velocity as shown by the graph. The position versus time graph shows a straight line, confirming constant velocity, while the velocity versus time graph remains constant, reflecting no significant acceleration, and this was for the computational model. So we can see how the velocity is constant as observed in the position versus time and the velocity versus time. And as observed here as well, this appears to be very constant as well. So that's how we know that all this that we have been talking about is true. So anyway, if I flip the axes, interchanging the positive and negative x directions, the results would have shown the same magnitude of motion but in the opposite direction. Instead of positive position values, I would have observed negative ones, but the velocity would still remain constant in magnitude. This highlights that the direction of motion is a matter of perspective and does not affect the object's behavior under constant velocity. In the model, I set the net force to zero, assuming no external forces like friction or air resistance, even though they were present in the real world. These forces slightly slowed down the object, but the motion was still close to constant velocity, which is why the experimental data is very similar to the computational model's predictions. And something that I forgot to specify earlier, the experimental, oh wait, never mind, my bad. So, as for how many forces contribute to the zero net force, the most likely forces acting on the bottle were 1, a small push or initial force that got the object moving, and 2, the resistive forces like air resistance and friction which opposed the motion. These forces nearly canceled each other out, resulting in a net force close to zero, allowing the object to move at an almost constant velocity. While the forces weren't entirely zero in the real world, they had such a small effect that the object's motion stayed consistent with the computational model's expectations. In conclusion, this lab demonstrated the motion of an object moving with constant velocity. By analyzing the motion using Tracker and comparing it to a computational model, I was able to confirm that the motion followed Newton's first law of motion. The predicted velocity was slightly higher, again, due to the assumption of no external forces in the model, while the real-world data was slightly slower because of air resistance and friction. Despite these small differences, the motion remained close to constant velocity, and the comparison between the model and observations was strong. Thank you so much for watching.